Hi guys, this is EasyElimu. I'm Vincent Kanmwai. I'll be your teacher for today. Stay tuned. Welcome. Today I'm going to take you through three-dimensional geometry, and we shall start with our first subtopic, which is geometrical relationship or properties of common solids. In this topic, we are going to learn about different relationships between lines and planes in 3D, and also how we can obtain angles using these properties, as we shall see as we proceed. In geometrical relationship or properties of common solid, we can start by given any kind of a geometry, we can tell in which dimension does that geometry lie. For example, if we have a line is a kind of a geometry, and it has properties whereby this line drawn this way, it is a one-dimensional geometry. And for example, if you have an area of any kind, any figure with the area only, it is said to have two-dimensional geometry. For example, you may have a two-dimensional geometry, or let me just write in short, a two-dimensional geometry may include we may have triangles. This is a triangle. We also may have circles only where we can obtain area. We can have hexagon. Let me just mention them. We have hexagons, parallelogram. We may have also rhombus, together with the others which you may encounter only where you can obtain an area only. They are two-dimensional. For example, like here, this is it is a triangle, and this is a circle. For example, we can obtain the area of this one, but it's only a two-dimensional geometry. Then we can move to another part whereby we can identify it, and it is commonly existing into our nature, and is known as a three-dimensional geometry, 3D now. In 3D geometry, we can view that in 3D geometry, we have different kinds of them. And these are those solids which have volume fully. We can obtain fully a volume, so it may include solids like we can have prisms, any of given. We can have also cone, pyramids, and so on, which you may encounter in your area. Maybe you can add octahedrons, we have sphere, and so on. Those are the three-dimensional geometry we may encounter in our ways. And these geometries are always identified, or solids are always identified by using either their lines, which can be either referred to as edges. You can also identify them using the vertices or the points. You can also identify them by also applying the faces which they occur. For example, the upper face, or the other way, or let's say not that face, but its face, the appearance, faces. So this one, it is planes. For example, if I have a rectangle, not a rectangle but a cuboid, a rectangle is a two-dimensional. So if I have a cuboid, If that is the case, this one is what I'm referring to, the plane or the face of that prism, the first face, the outer face. And then if we are talking about the lines or the edges, we are referring to lines like A, D. Line like AD, that is a line. AG, this one from that part to the other one. We are talking about GF and so on, as you can identify some of them there. And if we talk about the vertices, we are also talking about vertices A, that is the point where the 2 or 3 lines joins together. Now we have seen that A, at this point here, we have said that is where the vertices or the points are located. G, F, and also here where we find the corners is where the vertices are located. So we can identify a solid by either mentioning the vertices or the lines or even the planes. That is how we identify the solids of a given kind of a solid. With that, we can conclude the geometrical relationships or properties of a solid, and from there we can find out using several examples, and we shall see them while working out in our next sessions. Welcome back. We are going to see our next session, which is 5.2, and we shall be handling angle between a line and a plane. In an angle between a line and a plane, we shall view this with a relationship with using a rod and the sun as a source of light to view on it, such that if this is our plane, and here we have a rod, let's say it moves this direction. Actually, let me put it in another direction, like that. This is my plane. I have a plane A, B, C, D. That is my plane. Then I place a rod. Let's take a rod or a straight stick. From this point P, it stands up to Q. Then it is placed in a certain way. It lies in a diagonal way, such that the light or the sun is overhead it. The sun is striking it overhead. You will find that there will be a shadow formation on my plane, in that you will find, if this one is my line, my rod, I will find on which this point it will form a shadow. It will form a shadow. It will form a shadow in that way. That is my shadow, and that shadow, let's say, called PT. It will form a shadow PT, and that shadow is what we refer to as a projection, whereby PQ is bringing a projection on PT, because this PT is a shadow which will be formed when the sun is overhead, the rod PQ on viewing. So after the sunlight on it, overheadly, you will find that you have a projection which is formed PT. And from this projection, we can denote that actually it is in another direction. We can find that we will have something of that sort. We have something of that sort, and then we denote this one as P, and we find that our PT is a projection, while PQ is our rod. And on viewing that way, you will find out that using this plane, you will find there is a certain angle being formed between the rod and the projection PT. So the angle formed between PQ and PT is the same angle formed between the rod QP or PQ and the plane ABCB or ABCD. So if we want to find the angle between the rod and its projection, which is the shadow, is just the same as finding the angle between the rod itself, which is line PQ, and the plane ABCD. In general, we can just say that the angle formed between any given line and its plane, or any given line and its projection, is the same as taking the angle between that mentioned line or given line and the plane on which it lies. That plane, it's where its projection is formed, and that is the angle we should take. We can see it using our example. Then it is of length 8 meters. Its length here is 8 meters. And then we have its width being 6 meters and height is 4 meters. So having this, we can denote this point as A, this is B, C, D. Then we have PS, QR. PS, Q, R. And here we have also another line running from this point to the middle. We have that line, and it cuts SR at T. So the question was, or the information given was, a rectangular tank of length 8 meters, width 6 meters, and height 4 meters. SB is a diagonal, and we have found SB. Where is SB here? SB is a diagonal, SB from here to here. So it runs from here to this point. So up to there, that is SB. Is a diagonal of the tank, and T is the midpoint of SR. T. This T here is the midpoint of SR. So meaning, if the width is 6 meters, then from this point to here is 3 meters. The same applies to here is 3 meters because T is the midpoint. And then we are being told that calculate the length of SB. First A, we need length of SB. How can we find the length of SB? If you can view it very well, you will find that SB is forming something of the sort. You will find it is running from S to B, cutting the planes SRCD, this plane SRCD, the lower plane, and also touches the BC line. So we are finding the angle between line SB and the plane SRCD. What do I mean? We are going to have something of this sort. So we need that this is SB and is SRCD. That is a plane of which is in form of a rectangle. The base plane with the length being 8 meters, and the height, the width being 6 meters, and the height here we have 4 meters. So this height, the SB plane or the SB line is from this point to here, which we don't know what length is it. But remember, BC is 4 meters because it's the height of the tank, and 8 meters, which is RC, is the length of the plane which we have here as SR. We have SRCD. If you may move that direction, you will find we are talking about the lower plane, this plane which we are talking about. So we need the angle between the lower plane and the line CB. And here we were told to calculate the length of SB. Still, if it is the length, we can still find simply, whereby we can cut here first. First, let's move SB and take the rectangle. I have here S, R, C. This is D, this is C. This is a rectangle with the 8 meters as length, and this is 6 meters as width. And remember, in a rectangle, all the corners are 90 degrees. So, what I require here, firstly, I need the diagonal of this rectangle. That is the line I'm talking about here, the line SC. So, I need either SC or SC or RD. They are all equal. That is the line which I need here. So we shall, and we know what? This is a right angle. If this one is a right angle, then to find S, for example, let's find SC. If it's SC, we are going to consider a right angle triangle in that from this part, I'm going to cut this one in order to find SC. I'm going to cut that part, and if I cut that part, I will be having SCR, whereby the length is 8 meters, of which will turn to be our base, and the height of it will be 6 meters, which is the height of our triangle. And since this is a right angle triangle, then I'm going to use the Pythagoras rule, which we used in our trigonometry 3. So here we shall say that if we take 8 squared plus 6 squared, it should be giving us SC squared. And if we need SC, then we should find the square root of both sides, which implies that SC is equal to square root of, here 8 squared is 64. 64 plus 36, we are going to get approximate of 64 plus 36. So this one is going to give us 100, and square root of 100 is, square root of 100 is 10. So SC is 10 meters. So we have found that from this point to the lower point here, SC, we are finding that point to be 10 meters. So we can say that the lower part here, which is SC, we have 10 meters. So what here, we see the line SB. And SB, we are finding it is a plane, is a line which is a certain angle with the plane SRCD. But we are not interested with the angle first. What we need is the measurement of SB. Since we have found the measurement of SC and we have that of CB, we can still find the measurement of the other SB, whereby I'm going to cut SBC so as we may find it well this way. What I mean is here, I'm going to cut this measurement that way and then back here. so that I may find that one. And if I cut, I will find here is always 90 degrees. So here is 90 degrees from the deduction of a rectangle. And having that one as 90 degrees, we know this one we have found is 10 meters, according to what we have. And the other one is 4 meters. This one here is 4 meters. So we can comfortably calculate our SB, because we already have the base of that triangle, and also we have the height of the triangle, and we know that this one is a right-handed triangle. So meaning that SB is equivalent to square root of, according to Pythagoras theorem, square root of 10 squared plus 4 squared, of which is giving us, this is 16, 16 plus 100, you get 116. So let's see what it should give us. We are going to get 10.77 meters. So we can comfortably say that the length of SB from this point to here, we are getting it to be, which is this point, this one, we are getting to be 10.77 meters. And that is how we can use the relationship of edges. If you remember, in introduction of 5.1, the geometrical relationship between common solids or properties of common solid, we said we can use lines, edges, or vertices. And here we have used the lines of, or which is the edges. The property now we have used it, and we have found the edge or the line SB is 10.77 meters. Another question is the angle between SB and the plane CDSR. First question was to find the length of SB, and we have found SB is 10.77 meters. And now we need to find the angle between the line SB and the plane CDSR. This is the plane. So we said the angle between a line and its projection. The line SB has a projection SC. And if we need the angle between the line and its projection, then we shall find the angle between that line and the plane it falls on, or where the projection falls on. So meaning, from the diagram I recently drew, we need the angle between here. This angle. The angle between SB, the line SB and SRCD. That is the angle which we require here. But to get that angle, we have said, is the same as getting the angle between the line SB and its projection. And the projection of SB, we have said, is SC. So if we need that angle, now we shall find the relationship. We found this one to be 10.77 meters. This was our 4 meter, and this one was our 10 meter. So we can use any kind of relationship of the trigonometrical ratio and find out what angle is that. For example, we have all the measurements, so we can use any of what we want. I will choose to use the tan of the angle, which I may call it theta. And if it is tan of theta, it should be equal to the opposite of that angle. The opposite of the angle theta is 4 over the adjacent of the angle, and the adjacent is 10, which is giving me approximate of 2 over 5, of which is 0.4. This one is equivalent to 0.4. And if I need theta, I need to find the tan inverse of 0.4. And tan inverse of 0.4, I'm going to get is at 21.80 degrees. Now I can comfortably say that the angle between line SB and the plane SRCD is 21.80 degrees. From our properties or geometrical properties of a 3D or a common solid, we have seen that we can find the length and we can also find the angle between SB and the plane. So we can also find the length of AT. Let's find the length of AT. Let me remove the other dimensions so that AT may be well seen. Let's find the length of T. And if we need the length of AT, we have seen that T cuts S R into two equal parts. That is, T is the midpoint of SR. So meaning if SR is 6 meters, then S is 3 meter and TR is 3 meter also. So that means that if we truncate that one to pass through that point, we shall find that we are having that one as this side is 8 meters and the other one is 8 meters. So we are going up with a plane of this form, in that whereby this is ST and this one D and here is A. So what I'm talking about is this one, assuming that we cut this point into equals such that we have this plane. So the plane I'm talking about is that one, and we have known that if we cut that way, that one gives us a first triangle, a first rectangle, I mean. So if that one is our rectangle, I'm talking about rectangle ST, then let's just call this one not P, but let's give another one which is not here. Say Y. Let's call this part Y. So it will be ST, Y, then D to this point. So if that is the case, we can find the diagonal of TD, since this one is from this and we need the line from that part, we need that one. So to locate that one, we first need to find that one. And we know here is 8 meters. Here we have said it will be 3 meters because T is cutting SR into two equal parts. That is 3, 3. So we shall have that way. And if that one is 3 meters, we know for a rectangle, that one is making us to deduce a right angle triangle of the form SDT. So we shall have a right angle of the form SDT, whereby this measurement is 3 and this is 8. From here we can just deduce their diagonal very easily by taking the Pythagoras theorem, whereby this is 8 meters, this is 8 meters. So we shall say to find TD is the same as finding the square root of, from Pythagoras theorem, we remember we said if you take A squared plus B squared, you should get C squared. But if you need C squared, then you find the square root of the two added and squared sides. So this is 8 squared plus 3 squared, and you find out that TD is equivalent to That is 73 if you add the two things. So the square root of the two, 8.54 meters. I find that the distance from T to D, which is this one, we find that is 8.54 meters. So having that distance, and here we know it's 4 meters, we can also deduce out that here we have found is 8.54 meters. So meaning this one is 4 meters from the diagram as we have. So we can easily locate this one by finding using Pythagoras theorem, whereby this one is forming a right angle triangle with that line. So meaning we shall have, if we cut ADT, we are going to get a right angle triangle of this kind. This is ADT. So we are going to have ADT, we are going to have here is 90 degrees, and this is 4, this is 8.54 meters. So the remaining one, we just take also the Pythagoras theorem, and we said to find AT using the Pythagoras theorem. Now we shall take 8.54 squared. We find the square root of the sum. So we add to 4 squared, and that one we shall get it is 9.43 meters. So on addition of that one is going to give us 9.43 meters. So we are getting that the distance from T to A, it is 9.43 meters, this distance. So what I'm talking about is the distance from this point to the upper point, which is 9.43 meters. We have found the length of AT, and we can say the length of AT is 9.43 meters, and therefore the angle between ATD, the angle between ATD, having located everything on that ATD, we can still find the angle easily by using the properties of geometry of three solids, that is the vertices, edges, or the faces, which is the planes. So here we shall cut that what we want. We have been asked to find the angle between the angle of ATD, and we know the angle of ATD is just the angle between the line AT and the plane DCT, let's say YD. That is the angle which we require here. So meaning, if I may draw that one, we are going to have A here. I'm cutting this one out. This one is what I'm talking about. I'm going to cut it out. So if I cut that one, I'm going to get a right angle triangle that way. And this is D at this point. But here is 4 meters. Here is 8.54 meters. And then the other is 9.43 meters. And here it is T. So the angle ATD is equivalent to, we can say that we can use any of the form. Let's use tan of the angle, but take our angle to be like alpha. So tan alpha, we are going to get, it will be opposite, which is 4 over 8.54, and this one is going to give us, we shall find that tan of alpha is giving us 0.46838. So alpha, we shall find the tan inverse of 0.46838, and this one gives us alpha, or the angle between the angle ATD, as 25.09 degrees. Welcome back. We are going to see our next session, which is on angle between two planes. And here we are going to consider two different kind of planes which are intersecting on a straight line. And from these two planes, we can identify the angle between them, and we can calculate them by using the relationship between the two planes. And let's see. We have said that the two planes intersect each other on a straight line, meaning that there is an angle which will be found between the perpendiculars of the two intersecting lines on each plane. For instance, having these two planes, we have QRS, and at the same time we have a plane TQPU. These two planes intersect each other on the line PQ. And on doing that, we can find out that we have a line, if a line is cutting through SR and PQ at equal distance, let's say it is line NM, and we shall find that this line makes a perpendicular with the line PQ, meaning that it is forming a right angle at the point M with PQ. The same at this point and that one. The same we may have the line which at the same intersection which cuts plane PQRT at point LM. Let's say this one is L and this is M. So you find it also cuts that plane at that angle, meaning that you will find this one is a right angle and the other one is. So the line LM intersects PQ or cuts PQ at M, where they intersect with the line NM at the same line PQ. So meaning they are intersecting at where the plane is also intersecting. So if we are being asked to find the angle between two planes, generally we can angle by finding where the two perpendicular lines are intersecting on the plane, the angle between the two planes. For instance, if we need the angle between the plane SRQP and PQTU, we can find the angle between line NML. We can find that the angle between the angle LMN, which is equivalent to angle NML, is the angle between plane PQRS and plane PUTQ. Thus, we have seen that if you have been asked to find the angle between two planes, it is definitely being asked to find the angle between the lines which are perpendicular to each other and they are intersecting at a point which is on the intersecting line of the two planes as we have seen here. We shall see an example as follows. Let's consider this example, that is PQRS of a tetrahedron of 4 centimeter side each, and having line PM here. PM is M, and we also have QM. At that point, so we shall find that this one cuts this direction, and at the same time this one is 90 degrees to the other. So this line cuts this line at 90 degrees angle, as we have seen the same case to the other one. So we are being told to find PQRS is a regular tetrahedron of side 4 centimeter and M is the midpoint of RS. We have to consider this example. PQRS of a tetrahedron actually is a regular tetrahedron of 4 centimeter sides. So we have been told that M is the midpoint of RS, and we are finding that we have an intersection of PQ and also QM at RS. So we are being asked to do what? To show that PM is 2 root 3 long, and that show that PM 2 root 3 and triangle PMQ is isosceles. Triangle PMQ is isosceles. Triangle PMQ, this triangle, the other triangle, is isosceles. That is what we are required to show here. Actually, the other side is not present there. I just put it. It's a regular tetrahedron. A tetrahedron is drawn to that kind. In that case, we needed to show that PM is 2 root 3. And first we know this is a tetrahedron, and we have been told that M cuts line RS into 2 equal parts, or is the midpoint. So if this total RS is 4 centimeter, that means that RM is 2 centimeter and this one is also 2 centimeter. So we can find by denoting that we cut that plane. This is the solution. We cut the plane PRS, that is PRS. Then we put that M, which is the midpoint, and we know this one is perpendicular at the either side of that one, and we know this one is 4 centimeter, this is 2 centimeter, and this is 2 centimeter. So we can find the height of this triangle by saying that the height of which we don't know is the same as the square root of its hypotenuse, which is 4 squared, minus the base, which is 2 squared. And here we shall find that 4 squared is 16 and 2 squared is 4. So if you subtract, you are going to get 12. And this 12, it is square root of 12. 12 is the same as writing the square root of 4 by 3. It will still give you 12. And this one is the same as writing it as square root of 4 times square root of 3. And if you do that way, we are going to find that square root of 4 will give us 2. But square root of 3 will remain because it's a third form, so we shall have 2 times, actually it's 2 times square root of that one, which is the same as 2 root 3. And we have proven that this side is 2 root 3. So meaning PM is equal to 2 root 3 long, as they indicated we should show. Then here, we have been asked another question that show that triangle PMQ. Triangle PMQ. This triangle via the middle point and then up. So we have seen that this one is 2 root 3. We need also to find the downward part. And the downward part, we know this one is 4 centimeter. The other one is 4 centimeter, but here we don't know. This one is not known. QM we don't have, so we need to find QM. We need to find QM. And on drawing that, we shall find that also that one is going to give us this kind of a triangle, and of which this is 4 centimeter, the other side, the outside part, and this outer part is also 4 centimeter. And this is Q, this is S, and this is R. But here we have M. What I'm talking about is here. We have Q, which is on the top, and then S, if you pass through this line, and then you come back to R, as we have indicated. And then this M is the middle. And know what? It cuts line RS at the midpoint. So meaning this is 2, this is 2. The same applies. If we need the height of this triangle, we are going to use hypotenuse, and we have found this triangle is almost the same as the first triangle, whereby the height is equivalent to square root of 4 squared minus square root of 2 squared. Then this one we got is 16, square root of 16 minus 4, and it gave us square root of 12, which came to be 2 root 3. So we can denote that this is 2 root 3. But remember, the denominator is also, the lower part of this base is giving us 2 root 3. And we found here is 2 root 3. So we are deducing a type of a triangle whereby we have, okay, we have finished here, we can rub. We are deducing a kind of a triangle where we have, I'm going to draw this part, PM. So we have, let me start with this M. So I'll start with the M at the top, and then I draw this one, and then that one is going to P. So here is P, and I know this one is 2 root 3, this side, 2 root 3. And then I draw from M, I draw to Q, so it is going back to Q. And this is 2 root 3 also, as we have seen, and here is Q. So I will join the 2, and if I join the 2, is giving me this line, QP or PQ, which is equivalent to 4 centimeters. And from the rules of isosceles triangle, we have seen that side-side rule has worked, because this side is equal to the other side. So the triangle with the two sides equal, we call that triangle isosceles. We can find that is an isosceles triangle. Another question was, calculate the angle between planes PSR, planes. Actually, let me rub some of the unnecessary work. Show that we have finished that. Calculate the angle between planes PSR, planes PS is here, R. Now is this the outer plane, and QRS. So we are being asked to calculate a kind of Q. P. That's the plane we want. So we need the angle between the two lines. This one makes 90 here, at the same, that one makes 90 with the other. And we have found that this is 2 root 3, this is 2 root 3. But there is something we are missing somewhere. So we have been told to calculate the angle between the planes PSR and QRS. So we can find that if this one is a tetrahedron, it automatically means that this one we have found is 2 root 3. And this one also 2 root 3. That is the line which lies the slanting height of that tetrahedron. But we have a normal height which will be in between. In case for these two intersecting lines, let me just draw the intersecting lines whereby we have PM coming from top. This is PM, and I draw MQ, the intersecting lines, this way. M, that is MQ. We shall find that we need this angle, yes, but this one is the same as that one. This is 2 root 3, 2 root 3. But this one here, we found it to be 4. So, in order to find this angle here, we use different kind of method whereby we can agree to cut this point here. Because it's isosceles, we cut it into 2 to get 2 right angle triangle, whereby this is 2 centimeters, 2 centimeters, and we use one of it to find this angle here. And then after finding the angle, we multiply it by 2 in order to get the angle between the two planes, in order to get the angle between these two planes. And the angle between two planes, we said it is located by taking the angle between the two intersecting lines which are found on two planes and intersect at the line of intersection. For this case, we shall use this one, this measurement, and here we shall have, we have the hypotenuse as 2 root 2, and the base of the opposite of the angle we have 2. So meaning, if we have the opposite of the angle and the hypotenuse, we can use sine and let this angle be theta. So what we want is this two angle, which is 2 theta. So sine theta, it will be equal to 2 over 2 root 2, which is identified as 2 root 3 actually. We are getting it as 1.7321. So, meaning that theta is equal to sine inverse of 1.7321. Wrong calculation here. I'm going to get this one as 0.5774. So this sine inverse of 0.5774 and it gives us 35. So the theta alone is 35.27 degrees, and we need the two angles. So we take that theta, we multiply by 2, so we shall have 35.27 degrees, and we get the total angle being 70.54. So the angle between the plane PSR, the outer plate, and the lower plane is the angle between line PM and MQ. And that one we have found it to be this angle, which is 70.54. So we have concluded that we have found that. We can still find another one here. That is 70.54. We have found it. We can find the angle between line PQ and plane QRS. So the angle between this line PQ and plane PQRS. So we need the angle between them. And if we need the angle between them, remember from the previously, we have found that if this one is P, this is Q, this is M, we found that if we cut this way, we are going to find here is 35.27. This angle alone, the lower angle, we found is 35.27 degrees. The other one, 35.27 degrees. On addition, we got the total to be 70. But we need this angle because that is the plane which we are talking about. The plane of QRSR, the line PQ intersects with this plane at QM. So we need this kind of an angle. And to find that line or that angle, we need to take, this is 90 subtract 35.27, and we are going to get we shall get 54.7. So the angle between planes P, Q, the line PQ and plane QRS is now the angle between these two. This is the plane. The line PQ and plane QRS is equal to 54. We have found if you take 90 minus this one, we got is 54.73 degrees. And with the conclusion, we can say, having the knowledge of two planes intersecting on a straight line, we can find the line of intersection on which are located on the two planes, and from there we can calculate the angle of intersection between the two planes. At the same time, we can calculate the distances of the two or the lines given the angles. We are going to discuss about the skew lines. Skew lines are referred to as the lines which are on different kinds of plane and they cannot meet, but we need to find the angles between these two lines. We can find the angle between these two lines by either translating one of the lines to come into one plane of the given line where it lies. For instance, if we have let's take this is our cuboid. If this one is our cuboid with P, or let's say A, B, C, D, E, F, G, H, we can say like the lines which I'm referring to as skew line is line like this line G. Skew lines are G, GF, and that located on the other plane which is CE. We can find that if we take in other way, this one cannot meet with the GF, cannot meet with the CE because they are on two different kind of plane. The same applies to line AB and also line AB and line DF. They can't meet in either way. So you may be asked to calculate the angle between line GF and line CE. If you have been asked to calculate the angle between line GF and CE, for instance, what you should do, because the two lines does not meet or the two does not lie on the same plane, you should translate one of them to the other's plane. For example, you may take line GF to plane BCEH to be line HE in order to find the angle between HECB and CE. So to find that angle, what I do means this. You translate this line GF, for instance, translate line GF to plane BCE H. What I'm talking about is the lower plane. We translate it to that plane. After translating to that plane, then it will become to be line HE. If it is HE, then it is simple to find the angle between it. So that means if you need the angle between line GF and plane BCEH is the same as the angle between, now after translating, the angle between HEC. That is what we refer to as translating. You take one of the line which is not on the other's plane, you transfer or you translate it to the other's plane, then you find the angle between them. For instance here, if we need now the angle between GF and CE, we translate line GF or line CE to the upper plane or GF to the lower plane, and then we find the angle between them. For instance here, if we take now GF to be HE, we shall find that the angle between HE and EC, we shall find this angle, and it is for a normal cuboid is 90 degrees. The same applies to any kind of skew lines. Thank you. Thank you for watching. This was three-dimensional geometry, and I find it much more interesting. And it's quite simple if only you understand the basics of geometry, which we learned in both Form 2s and so on. And if you understand very well, you will find it easier working it with these formulas, and also after understanding trigonometrical ratios. Thank you very well, and I think you will understand much more about the trigonometrical ratios and tackle some of the examples and also in this 3D geometry. Thank you.